Hello guys, I'm Sandip. And if you do remember in the previous session, we have started the chapter light. We have seen some introductory part of the chapter light, how light travels, who are the sources, right? Luminous, non-luminous object. We have seen that much. And we have seen about the transparent, translucent, and which one is the last? Opaque, right? So we have considered all those objects too, right? What they do, what are their properties, who allows the light. Now we have whole idea about that, right? So today in this chapter, in this session, we are going to see some mirrors. Right? Mirrors means we already know about the mirrors, right? Plane mirror. We have that plane mirror in our home, right? So let me ask you one thing. There is one place, if you do remember, where you can see the maximum mirrors. A lot of mirrors are there on almost every wall, right? Can anybody guess which is that place? A lot of mirrors. Almost on every wall there is a mirror. Right? There is a salon, we can say salon, where we go for hair cutting, right? So there are many mirrors. Have you seen one in one of the mirror? Consider two walls, opposite walls there, right? In front wall, you can see yourself, and there is also wall mirror, I can say, in the opposite face also. Have you ever observed there are a lot of images just starts forming, and you can see yourself for a lot of times, right? Many images form there, infinite number of images form, we can say, in those mirrors, right? So those are the properties of mirror and how the mirrors work. There is some reflection. What the mirror reflect, mirror does not reflect the object, right? There are no two objects, there are no two times of you in the mirror, right? One yourself and other is your, I don't know, your twin. No, that is not going to happen, right? That is just the image. We can see ourselves in the mirror. Who is making it possible? How we can see the mirror? If you do remember in the previous session, I asked you the first question, how we can see the object, right? The answer was very simple. First, we'll need the eye, and the second thing is light, right? Object reflects the light from the source to our eyes. That's why we saw the object. Now, this time I'm asking you another question: how we see the image of ourselves in the mirrors? Okay, so obviously we need the eye. That's correct. Do we need the light? Yes, that's right. We need the light also. And the mirror is the object, we can say, which has some special property to reflect the light. Even object reflect the light. But what is the property of mirror then? Everybody can reflect the light, right? Object can also reflect the light. But mirror reflects the light, we can say, in some special way, according to some angles. We can say particular angles are there, right? Then we can get the exact opposite view of whatever is the object, right? So one is the object, and second is the image. Image is created by the plane mirror or any kind of mirror. Normally plane mirror, we do see the plane mirrors everywhere, right? In our home also we use the plane mirror. What are the different types of mirror? Right, so there are some spherical mirror, right? Where have you seen some spherical mirrors? Right? Spherical mirror means what? Consider a whole sphere. Here we can see one sphere on our screen, right? It's can I say that sphere is transparent? Yes, that sphere is transparent actually, right? But consider if you silver the surface. Silver means what? Remember this part. Whenever we are dealing with the chapters of this slide, always remember silvering. So if you consider, if you take any simple glass, we know the simple glass is transparent, right? It is going to allow some light. So consider if the light goes here, that this is the transparent surface, glass is transparent, so it is going to let light pass as it is, right? Now, if you silvering means what? One part of this glass, silver it, right? Then what is going to happen? Whatever light is going, it is coming back into the reverse path, right? So it is going in a straight line, obstruct to the mirror, and it comes back as it is, right? Now this object becomes the mirror. Similar, if this is the spherical part, if you silver it, this object's mirror become a mirror, but it is not a plane mirror. This I can call it as a plane mirror. This becomes the spherical mirror, So can you, you do remember in the last session, as I told you that in circus or in Imagica, some kind of places, fun places, there is one room of the mirrors, house of mirrors, we can say, they can say, right? Palace of mirrors, etc., etc. There are a lot of different shapes of mirrors are kept. Plain mirror we do daily, we see the plain mirror, right? But what happens in those type of mirrors, spherical mirrors, mirrors which are actually concave, different shapes are there. If you see in those, the reflection of yourself is not accurate. It shows you the distorted image of yourself. It could be you could become fat or slim because of those mirrors, right? Because spherical mirrors are not giving you the exact representation, right? So why to use the spherical mirror? If they are anyway not giving you the exact reflection, then why should we use those mirrors, right? So those mirrors also have some properties, right? We can say they can magnify object or they can make the smaller size, right? Plain mirror is not going to do anything. It is going to show the image of yourself as it is, right? But spherical mirrors have some properties and those are obviously useful. For example, if you consider the mirror on your bike or a car, right? What you can see actually in those mirror, you can see the back bikes or cars which are coming from vehicles coming from the behind you, right? That is needed obviously, right? So observe one thing in that mirror, that if you closely read on that mirror, there is one sentence written on that mirror. The mirror says objects appear in mirror are closer than they look. This is the one very important notice they have written on that mirror. Do that thing. You have the bike car, go outside and try to observe that. Right? They have written that thing. Right? Objects appear in the mirror are closer than they look. Means what? What is the meaning of that? You can see the any car in that mirror. So can I say that size of that car is very big behind you, but in the mirror you can see very small size there, right? But it is also very close to you, but you can see it is very far away from in the mirror. That's why they have written that notice, right? Because according to mirror, it is very far away, but it's not the actual case. That car or that vehicle is very, very close to you, right? So that's the caution they have written there. Okay. But obviously, you cannot, you wanted to see everything which is behind, which is going behind you, right? Or which is coming from behind. It's behind of you can say, right? You cannot just, you don't want just to see the whole image of the car, how the car looks like, it's actual image. You wanted to see a lot of maybe 2, 3, 4, 5 vehicles coming from the behind, therefore those size becomes very small, and those are the uses of the spherical mirror. You cannot just put the plain mirror there, right? Plain mirror will give you the actual size, so you can only see the one vehicle there. That's not good, right? So these are the uses of the spherical mirrors. Okay. So today let's study those plane mirrors as well as spherical mirrors and how the images got formed. Right. So, so today what we are going to cover, laws of reflection. Reflection means what? Those mirrors are giving us some images there from the objects. How light is getting reflected there. Therefore, we are getting some images there. Okay. Then images formed by the plane mirror. We know that now that the image is, it shows the actual you in the mirror, right? It is not going to distort your image. And images formed by the spherical mirror, as we know that now the spherical mirrors, they do what? They change the shape or they distort the image. They make it smaller or bigger in some cases also, right? So according to the different mirrors, different shaped mirrors, we can say. And mirror formula is also there. Mirror formula means what and why it is useful for us? You can consider one thing there, as we talked earlier, that when we say the car or vehicle is behind us, and I also told you what is the caution written on that mirror, that objects which are seen in the mirror are closer than they look, right? So simply consider this is the mirror kept here. You are driving the car like this, you are sitting in the car, right? You can see the other car in this mirror, right? something here, somewhere here. This is the other car in the mirror, right? Actual the car is closer, right? That's why they have written that. So consider this is the car, small car, at some distance from you, right? You are in this car. Let me draw the correct, better car for you, right? And this is the mirror, right? This is a small mirror here. I want to zoom it. Mirror looks something like this. So in this mirror, you can see this car, right? So let me put this mirror here only instead of taking it far away. Just I will zoom this mirror and here only, right? I will keep it here only. So this is the mirror which is zoomed actually. Mirror is actually very small compared to car, right? We know that part. So consider this car will look something like this in the mirror. Right? Okay. So this is called as the object distance. Actual distance is called as object distance. But what you feel in the mirror, that car is very, very behind, right? So whatever distance you feel, it's called as image distance. So how to find out what is the object distance and what is the where the image will form, what will be the actual distance there, right? So for that we are going to use some mirror formula there, right? That will be very useful for us. Okay, sure. So let's start with the laws of reflection. So laws of reflection means what? You can see this is the mirror which is kept horizontally. Normally we have the mirror attached to the our dressing room or cupboard, we can say dressing table. So if this is the mirror, we stand in front of mirror like this, right? And you will see the image inside the mirror, right? So the image will be, let's say something like this, right? It will be exactly opposite to you. Okay. So now consider here they have kept the mirror like this horizontally. So if consider if I keep any object here, what will happen? I will get the image somewhere here, right? Inside image we can say. But actually, images, this is inside image is called as virtual image. It is inside. Now virtual means what? Not real, right? So normally when we are going to say that light is coming, right? So light, obviously light is going to give you some image, right? So instead of person, let's say I kept some object here. What is going to happen on this object, right? So consider if there is some source, we need the source for the light. Let's put some big bulb here. What will happen? Light will come here. This object is going to transfer the light on the mirror. And from this mirror, it is going to get reflected like this here. Okay. So same thing is represented in this ray. So this is nothing but the light ray. So if this is the object, light coming from the object cannot give the emit the light itself, right? It is actually going this light from somewhere else, like this object, right? Bulb or tube light, we can say. So this is the light. Let's call this as incident light, right? Here you can say incident light or incident ray. And the light is going to get reflect like this. How to show? So first of all, what we can do, just draw one perpendicular like this. They have drawn it here, one perpendicular, which they have named it as normal. So this is the perpendicular to the mirror. Okay. And whatever angle you can see here, let's say 30-degree, right? Reflected ray is going to make similar angle like this. So this will also be 30-degree. Right? So whatever object incident light is coming, it is getting reflected in the same angle, we can say. Okay. So what you can see, if you are observing from this side, let's say, right, you will see this object reflection here, right? And you will feel, you are going to feel that this object is inside this mirror, right? Let me draw this diagram a little bit upward. So I will draw a small scale diagram here now. So this is the incident ray, this is the reflected ray, and consider this is the observer you are watching from here. What you are going to fill, the object is here, right? And that is we can call it as image actually, right? So I can say this is my object and this is my image. Okay, so this is how the reflection works. This is how we can get the image. Okay, so here also I can show it here, right? Let's see what is going to happen. This is our object kept here, right? So this is the incident light. What we want to do, first of all, draw the perpendicular. Perpendicular's name is normal, right? So draw the normal. If this is making angle, let's say theta now, right? Incident ray will be shown like this. Arrow you can see at the towards the normal, right? So if the ray is coming, you can show the arrow like this. So at this point, it is going to get reflected. This is called as reflected ray, and arrow will be like this. And where is the observer? Observer means we can show the observer by this eye. So observer is here. What is going to think? This ray is coming towards his eye. So you can just take this ray away from here, and he is going to think that object is here. Sorry, image is here, right? So this was our original object, and for the observer, this will be the image. Okay, along the, or we can say opposite side of the mirror. So this is the whole principle of reflection, we can say. Okay, so let's see what are the laws of reflection. First of all, reflection's definition is very simple. What they are saying, here you can see, when the ray of light approaches the smooth polished surface, the light ray bounces back. Right? Normally, I told you silvering part, right? Or the plane glass, silver it from the one side, one plane, we can say. Then you are going to get mirror. So when the light approaches this silver mirror, we can say, and the light ray bounces back, it is called as reflection part or reflection of light, we can say. And what are the laws of the reflection? Right. So first law you can see here in the incident ray, reflected ray, and normal. We now know all those things, right? What is incident ray? Actual ray coming from the object, we can say. What is reflected? After making same angle, it is going to after making same angle again, and to the normal, we can say. So normal is also important for us. So incident ray, reflected ray, and third one is normal. So all these three guys should be in the same plane. Incident ray, reflected ray, and third one is normal. What is normal? Normal is nothing but perpendicular drawn to the surface of the, we can say, plane mirror, right? Okay. So all this should lie in the same plane, right? At the same point, same incident. Right? So incident ray, reflected ray, normal to the reflection surface. And the point of incidence means this is the point of incidence, right? Where they meet actually, lie in the same plane. Okay. So this is the first law, we can say. Let's see the second law. So this is the second law. Let me mark this as second one. The angle which the incident ray makes with the normal is equal to what? Angle which the refracted ray makes to the same normal. Right? We know that 30 degree. I have written here. Theta, I have written here, right? So angle, incident ray and reflected ray makes with whom? Makes with normal should be equal. Very simple. So tell me one thing. If the incident ray is making 45-degree angle, what should be the angle of reflected ray with the normal? Right? Again, 45, same angle. Okay. So these are the two laws of reflection. They may ask you in the exam. First law is what? First law says that three objects, we can say. Incident ray, then reflected ray and normal. Let's call them as friends, right? Three friends are there: incident ray, normal, and reflected ray. These three friends are lying together in the same plane, right? So this is the first law, and second law is what? Angle of reflection and angle of incidence, or we can say angle which the incident ray makes with the normal and angle with the reflected ray makes with the normal are what? are similar. Okay, very easy to understand. Then let's move to the next one. Image formation by the plane mirror. As I told you that observer is also important, right? So whatever light observer is getting reflected, right, then we can decide where is the image's position. Right here, when cool animation is there, right, what they are doing, they are moving the object. Consider object is, let's say here at the start, or yeah. So then you can see the light is something like this, right? So if this is the light for observer thinks that object is inside, and this is called as image. So if this one is the object, this one is the image. And you can see the positions of the object. If the object is here, right, observer think image will be here, right, like that. So according to the observer, position of the object, image will change, yeah, wherever we keep the object. Now consider if the object is kept in the front of observer. In front of observer means, or we can say objective observer is itself a object, means person looking in the plane mirror. You can see the exactly opposite, you will get the image there, right? So these are some simple formation of the images by the plane mirrors, we can see. Okay, then let's move to the next part. Then we are going to talk about the spherical mirrors, right? So in spherical mirrors, there are two parts, two types we can say. One is called as concave mirror, and one is called as convex mirror, right? So which one is concave, which one is convex? How to remember that part? So consider if this is this. Consider I have taken the spherical glass like this and polished this part. Here they have represented it by hard surface. Means this part, inside part, will become reflective. So can you see here? They have written it reflective surface. Okay. This mirror we are going to call as concave. How to remember this? Cave, we know the cave, right? So it is something like going inside the cave, right? Therefore, we are calling it as concave. Okay. Can you say it is also cave? No. Why not? Because we are polishing this. Now, initially you can say the shape of the glass will be same, but polishing is going to decide whether it will be a concave mirror or convex mirror. Now consider silver this part. Now, what we can say, observer will go from here. Now, is it a cave for observer? No. So this is the hard surface. Which one is the reflective surface? This one, this part. So mirror is from this side. Okay. So this is the mirror. For this is the mirror, this side. Okay. So obviously concave means what? We are going into something like we are going into cave, we can say. Therefore, this is concave, right? And the other one will be convex. There will be some we can say this is called, this is the depression, right? It is, we are going into the depression, we are going into the cave, therefore it is concave. And this is the elevation, we can say, right, from the center, or rise, right? So this is called as a concave, convex mirror. Okay, so how the images do look in this concave or convex mirror, we also have to find those things, right? So let's see on that. So where do you see this concave or convex mirror? If you do remember, I told you at the start that our car has a mirror. It is not a plain mirror, obviously, right? It is a convex mirror actually. Also, if you do visit some malls, in malls also there are some mirrors. They do look like sphere, and they are coming outside of the mirror, we can say. They are not our normal plane mirror, right? They are coming outside of the surface, we can say, little bit. There is some elevation, we can say, some rise in the surface, because those are convex mirror. Why those are convex mirror? Because convex mirror can cover a lot of area instead of plane mirror, right? So using those mirror, the owner can see lot of space, whatever everyone is doing in that mirror, right? Normally nowadays we use the cameras also, right? Cameras are the very secured thing, we can say. Those mirrors are also going to provide you lot of coverage there, we can see, right? Okay, so these are some use of the concave and convex mirror. Concave mirror, where we use normally in And normally for saving purpose, we can use the concave mirror. Normally, we can also use the plane mirror. That's not a big deal. Concave mirror is also one solution. Or a dentist use the concave mirror sometimes, right? So they have a very small mirror attached to their that small rod, like, which looks something like a spoon, but it has some very small mirror on front of it. Right? So dentists use the concave mirror, we can say, right? So these are the spherical mirrors and uses. Now let's see how they works. Okay, so what is going to happen in this case? Let's talk about the concave mirror first. So there are some parts we should know about these mirrors. So this point is called as pole, right? And you can say this is, can I say this is the part of the circle, right? If I complete this circle like this, it will be like this, right? So there is one center also there for this mirror, right? So this point is called as center of curvature. Center of curvature. And the distance is obviously radius, we can say, right? This is the center of curvature. Okay, distance is represented by radius r, we can say. Then there is another point you can see. What is that point's name? So let's see a little basic of this rays coming onto this mirror. We know there is rays are the one who are actually giving you the providing you the image, right? So what happens in this case? So let me this one. So consider some rays are coming from this objects, right? We know the rays comes from where? The different objects. So in the rays is coming like this, right? Another ray is coming like this. Let's say here also some rays are coming. These rays are going to reflect here. Why? Because it is a mirror. Mirror, what is the purpose of mirror? It is going to reflect some light, right? So it is going to reflect the ray like here. This is also getting reflected. Every ray after reflection is going to pass through one common point. And this common point is very important for mirrors, which is called as focus, denoted by F, and distance is also denoted by F, right? And this point is called as focus point, where all the reflected rays are going to be, right? So this is the one of the property which making the spherical mirrors very important, that plane mirror could not provide. For plane mirror, what is going to happen if some parallel rays come like this? They will go back, right? For parallel mirrors, remember, if the lines come like this, they will go back something. They will never meet. But in this concave and convex mirror, they are going to meet at some particular place. That particular place is called as focus point. Even in this concave convex mirror also, you can do the same thing, right? What is going to happen? These are the rays coming. Right now, in this case, what is going to happen? They are going to, the reflected rays, remember, they will look something like this, right? Because this is the mirror is going to reflect the rays, right? Now, if you do remember, we also talked about the normal, right? So for plane mirror, there is a normal perpendicular. Similarly, I can also say here, the normal is perpendicular to the point, but as this is the spherical mirror, normal will also going to look different for every point, right? So here the normal will look something like this. Here the normal is going to look something like this. Here is also normal. We can draw the normal for every points. And the rule is same. Whatever is the angle of incidence, here you can see if the angle of incidence is theta, angle of reflection should also be theta. For every point, here also theta. In convex mirror also, if this is the angle theta, this angle should be theta. Right? This is also theta, this is also theta. But what is the difference between concave and convex? Here you can see for concave mirror, they are meeting on the same place, right? At the focus. Now these rays in convex mirror, what is happening? They are going away instead of coming closer to the mirror, right? So what we do in this case, there is some modification we do, right? So these rays are going away. So we can actually extrapolate this here. Just imagine like they are going behind the mirror and now they're meeting here. So this point we can call it as focus point. Okay. So both concave and convex mirror have focus point, both have radius of curvature, both have obviously radius, they are spherical mirrors, right? And there is one relation also you should remember between focus and radius of curvature, that is R. Very simple relation. You can say F is equal to R by 2. Remember this relation. This is going to be very useful for our upcoming session, we can say, or some numericals if you want to solve. F is equal to R by 2. Okay. So this F, focus and radius of curvature, as I said, both are going to be very important for us for solving some questions or numericals, we can say. Okay. So these are some things, some terminologies we should know. What are the terminologies? Pole, I have said for this mirror also, I can say this is the pole, right? Then we also know what is the focus point, what is the distance F. Distance F means what I can say, where all reflected rays meet. Reflected rays meet, right? And the distance is what? Distance or focus length means what? This is the focus point. And I can also say for focus length, what is the focus length? The distance between pole and focus point. Simple. Okay. So this is the focus point and focus length, we can say. Then once we know all these things, center of curvature, right? Center of curvature represented by C. Also remember this part, right? Okay. So all these things we know. Now let's find out how the image appears in front of those type of mirrors, right? We know that these mirrors are used in where? In the car to look vehicles coming from the behind, then in the malls, right? So in the at the dentist shop, right? So let's see how these images work, where to keep the object and etc. Right? So consider this is the concave mirror, right? You can see concave means this surface should be polished. Concave, so inside, going inside the cave, right? Like this. So this is the focus point we talked about. This 2F length, this is the 2F length, right? So I can say this is the F length and this one is 2F length. 2F length means what? Can I say this is the radius? Yes, radius is double of the focus. And let's call this point as F point. And let's call this as C point. And this is our pole, right? Pole is here. Okay. So according to the distance, we can say object, wherever we keep the object, there will be different possibilities of the images we are going to get, right? For example, if you keep the object at the infinite position, right? Let me draw one mirror also here, right? This is the very good animation. You will get very things clear here. So consider this is pole, this is focus, and this is center of curvature. If the object is very at an infinite position, we can say, right? We will get some rays like that, and those rays are going to pass through, right? So normally what we have to do to draw the ray diagram, draw one parallel ray which is going to pass through like this, and draw another ray which is going to pass through focus. This so these are two incident rays, right? We know the incident ray, reflected ray of the parallel ray is going to pass through focus. If we draw the incident ray from focus, it is going to go parallel like this. Okay, so this is the condition to draw some ray diagrams. We are not going to go into the detail of that right now. Right? So just remember, we will get the different positions of the images. So if the object is at infinity, we are going to get image at the focus point here. Right? So let me draw one small table. So if the object, this is image, right? The object is kept at infinity, we are going to get image at focus point, means distance F. Can I say distance F? Yes. So let me call this as object distance. and this is image distance. Object distance is represented by u, image distance is represented by v. So if we keep the object at infinity, we are going to get the v at f. Okay, then what happens if you keep the, you can see in this diagram also, this object is running, right? Consider from infinity, we are here, it was infinity, right? Object was coming there. Now closely observe when the object is kept on the center of curvature. This yellow color is going to represent the image, right? So closely observe and think on that. If the object is kept at the C point, where we are getting the image, right? Can you see, is it at the perfect at the C? So if the object distance is C, C means we can say R, right? R is our radius of curvature, or 2F we can say, right? Image distance is also R. Right. Consider if we are keeping the object, let's say between C to F, right? What will happen? Image, you can see the, where is image? Image will be is beyond center of curvature. So consider object is kept from C to F. Image will be beyond C, we can say, right? Right. What happens if you keep the object from infinity to C? Object will be where? From focus to center of curvature, we can say. Similar, if you keep the object at F, you can see, look at that, right? F, if the object is at F, image goes to infinity. And there is one more point, F to, let me write it another here, F to infinity, F to pole, you can say. So consider, find out, look very closely where the object is going when we keep the, where the image is going, we keep the white colored object from between this focus to pole, right? You can observe it, it is going into the other side there, right? Other side means it is called as virtual side or behind the mirror. Virtual, this part is called as real, this is behind the mirror, and this is in front of mirror. Okay, so if you keep the object between focus to pole, the image is going behind the mirror, or it is a virtual mirror, we can say, right? Like this. So let me write this as behind the mirror. There are some one small table we can find out, right? One more thing we should remember in this terminologies, let's consider, let me cancel this one. If you keep object any place, at any place, okay? So consider this is your object. Object's distance is called as u, like this, right? And image you are going to get here, we can call this as v, right? There is one sign convention also we should remember. Sign conventions. Sign conventions is that from the pole side, this is the left side, right? For the pole, and this is the right side. Distances in the left side, distances in the left side should be taken as negative, and on right it is positive. Similarly, upward on this axis, this is called as, let's say, principal axis. Let's call this as principal axis. So distances upward, we can take it as positive, and distances which are downward, we are going to take it as negative. Okay, so these are some sign conventions we are going to remember, right? So according to that, we can solve the questions also on this spherical mirror. Okay, so here you can see object was at infinity. This is the pole, right? For this pole, this is the left side. So every distance which is on the left side of the pole will be what? Negative, right? This is negative, I can say, and this side it will be positive. So only when I keep the object from focus to pole, in only that case what I'm getting, image on the behind of the mirror, behind means virtual or right side. So only that time I'm going to get the negative distance for the image. In all other cases, object is anyway we are keeping on the left side. So we can consider negative distance, and object distance is denoted by what? U, right? Small u. And image is also we are getting on the right side if we keep it beyond the focus, obviously, right? Also that will be also negative, right? Okay, so this is the case we can say. And you can also see some sizes of the object, right? Object is obviously, object size is not going to change, but image, can you see that image, that yellow color arrow is changing its shape? Have you observed that, right? So first of all, that yellow color, when it was on focus, it was very small, then it is increasing its size, right? You can see here. So these mirrors, concave and convex mirror, not only shows the image or change the distances, but it also changes the size of those, which is called as magnification. Right? So if the, here you can see the that arrow is getting very big after this, after it reaches the C point, right? So it gets magnified, its size enlarges, we can say, right? So magnification's formula is height of image upon height of object, you can say, or minus sign I will give here. There is one more formula, minus V by U, right? So if you know the, what is V? V is image distance, right? Image distance, and this is object distance. Okay, so this is another formula for magnification of the concave mirror, or we can also use those, the same formula for convex mirror too. Okay, so these are the concave mirrors or formulas, we can say. We also found out one table also there, right? Okay, sure. So next, and image formation by convex mirror. Now convex mirror, there is only one condition, remember. If you, wherever you keep the object, in concave mirror, what we have seen, if you change the position of the object, then everything is going to change, right? Its size is going to change. It is always it will be sometimes in front of mirror, that is real, we can say, and sometimes behind the mirror, it was virtual sometimes, right? But for convex mirror, doesn't matter where you keep the object, whether it is at infinity or center of curvature or focus point, every time image will be on the behind the mirror. Remember, this is behind mirror. And also you can say it is virtual, right? Behind the mirror means what? Virtual. Or I can also say this is smaller size. You are always going to get smaller size. Okay, so magnification's formula is same, minus V by U minus HI means height of image, HO, that is the same formula. But in this case, remember, U means what? U means object distance, it is going to be negative. And this is image distance from the pole, obviously, V is going to be positive. So these are some cases you should remember while solving the problems for concave and convex mirrors. Okay, and we have seen that concave mirror is always going to convex mirror is always going to give you this type of image. There is no change in the image wherever you keep the object, and it is always smaller, right? So therefore we use that convex mirror for our car, because therefore the image of the car which is behind you, right, it is smaller, not bigger, right? So it's like that. So if you want to magnify the image, means to get the bigger image, you cannot use the convex mirror. You will need the concave mirror. But in our daily life, we don't need the bigger image. Normally we use this convex mirror most of the times. Where you will need the bigger image? As I said, a dentist use the concave mirror. Why? Because they need the bigger image of whatever is inside the teeth, right? Therefore they use the concave mirror. But normally in case of car or in mall, I have told you, those mirrors need the smaller images, right? Like that. Therefore we use the convex mirror there. Then now let's talk about the mirror equation. There is one formula we are supposed to use, right? So consider this is the concave mirror. I can see, you can see u is what? Object distance. Then where is image? You can see how to find out the image. First of all, draw one parallel ray. It is going to pass through the focal point like this. Then draw another line which is passing, incident light is passing through focal line. It will connect here. Then draw a parallel reflected light. Simple. So what you can remember here, if the line is parallel, incident ray is parallel, reflected ray is going to pass through focal point, right? If the incident ray is passing through the focal point, reflected ray is going to pass through pass parallel, you can say, right? Initially I said something mistake, I guess I have done. Yeah, if the incident ray is parallel, then reflected ray is passing through focal point, right? I said the incident there, it should be reflected, right? And the incident ray is passing through the focal point, then we can say reflected ray is parallel, okay, like this. And u, v already we have talked. V is what? V is the distance of image. Using this, what we can calculate? If I have the u and v's formula, I can calculate m is equal to minus v by u, right? That is magnification. So what is going to happen in this case? You can see object is here. Object size and image size, you can compare. Image is becoming smaller. Remember, if magnification is 1, object height is equal to image height. Both will be same. So plane mirror doesn't change our sizes, right? So can I say magnification of plane mirror is 1? Yes, that's right. If the magnification is greater than 1, means HO, height of object, will be less than image's height. Magnification means what? Even in our mobile, there is camera. In camera, we zoom it, right? We zoom it means what? We are magnifying it. Means image size is, that photo size will be greater, right? Bigger, we can say. Therefore, height of image will be greater. If EM is less than 1, in this case, object size will be bigger and image size will be very smaller, you can say, right? So in this case, object size is bigger, image size is smaller. Okay. So who will give you the exact size of the image after, if you know the object size? This formula. Okay. Sure. So there is one mirror equation also we should remember. Now we know what is here, then what is u, and what is v. We know all these concepts, right? There is one more concept you should remember about this focus point. You can see the focus for the convex mirror is on where? On the convex mirror. Maybe everything's there. Remember, even though the rays are meeting here for the convex mirror, focus point will be here, right? You can assume this condition. If the incident ray is like this, reflected ray will be like this, right? And after reflection, we can assume to meet them here. So just remember here in the case that focus point in concave mirror is negative. And why negative? Because it is on the left side of the pole, right? And for the convex mirror, focus point is positive. We should also remember this while solving some questions. Okay. So focus U and V. And as we know, we have to use the sign conventions. Sign conventions are also important thing for us. Okay. Sure. So this is the basic theory of your spherical mirrors. Okay, let's try to solve some questions now. Consider what is the height of image of person whose actual height is 1 meter. In, let me add something to this question, in plane mirror. So he's looking into the plane mirror, right? What will be the height? Right? We know the plane mirror doesn't change anything, right? So whatever is the height of actual height of the person, image height will be same, right? So can I say it is 1 meter, right? Very simple. Then under which of the following conditions concave mirror can form real image larger than the actual objects? Where to keep the object, then we are going to get the larger image. Let's find, look at this animation. In this animation, we need the larger size, right? Where we are getting the real larger size. They also mentioned the real image, right? Real means here only. So don't consider this part. Even though we can see when the object is at EF to P, image was bigger, then it is going to get smaller, smaller, smaller. But don't worry about this part, right? So we just have to worry about this part. Consider at the infinity, image was very small. At the center of curvature, if you look closely, the object and image will have the same height. Right? At the center of curvature, it is inverted, right? It is not real. Sorry, it is real, but it is not, we can say, upside. It is inverted, downside, you can say. But we are just worrying about the size now. At the focus to center of curvature, that yellow bar was very small, yellow arrow, right? When it is moving from center of curvature to infinity, then it is going to get bigger. So where we kept the object for it to get bigger, you can see whenever that arrow is bigger, the object is where? From center of curvature to focus, right? Can you see that? So simple. Where to get it? Between focus and center of curvature. Find out where it is. First object say distance equal to radius of curvature. No, right? It will be a same size. Distance less than focal length. No, it is not going to give you real image. They are asking us the real image, right? In this case, we are getting the virtual image. Object must be placed between focus and center of curvature. Yes, that's right. Right. So we don't have to worry about the last option, right? Yes. Then we need one formula also here, mirror equation, right? So I forgot you to give you the mirror equation. There is one very small formula, simple. 1 upon Vf is equal to 1 upon V plus 1 upon U. This is the mirror equation, we can say. We are going to use this equation in one of the problems, right? So that will get clear. But remember, whatever sign conventions are there, we are supposed to use those, right? U is negative on the poles left, V is negative in all the poles left, EF is negative for concave, and EF is positive for convex. We should remember those parts too while solving the numericals. Now let's see. Move to the next question. Magnification produced by the rear view mirror fitted in vehicles are. Magnification means what? Whether it is making smaller or larger, right? Obviously, we know that size of the car we see in our mirror is small. For smaller magnification, capital M is what? Less than 1 or equal to 1 or greater than 1. We have written that part. Let's see. For object to be smaller, right? Means height of, image is smaller. So height of object is greater than height of image. In that case, magnification is less than 1, right? So write down less than, this is less than 1, right? Now, this is one numerical where we have to use this formula, right? We have written this formula, 1 by F is equal to 1 by U, 1 by V. Okay, so let's try to use this formula. A 10 long all pins, that pin we use to stick anything to the board, right? So pin looks something like this, which has a pointy head, right? Thumb tack, you can say. Okay, so this is the pin. It is placed vertically in front of concave mirror, right? Concave mirror is like this, and a 5 long image of all pin is formed at 30 centimeter in front of mirror. In front means what? Here, right? Images distance they have given from the pole, right? Images distance means what? V 30 we can say. Let's take it 30, right? 30 centimeter. On in front means what? On the left side. Left side means negative direction, right? Negative sign should be taken. Then 10 millimeter long means height of the object. Pin is kept here like this. So height of the object is given as 10 millimeter. Then what else we have? If 5 long image is formed, means what? Height of the image is 5 So what we can calculate from this? Magnification, right? And V is also, we also have the V. And they are asking us the focal length. This is the formula for focal length. What I will need for focal length? V as well as U. We have the V. We don't have the U. So how to calculate U? Use this formula, magnification. Magnification is what? There are two formulas there, HI upon HO, or minus V upon U, right? So using this formula, let's we don't need this CM, right? Minus sign will get cancelled. So can I say simply HI upon HO is equal to V upon U, right? Very simple. Let's substitute the values. This is 10, this is 5, V is given as 30 or minus 30. Let's calculate U, right? So if I do some simple calculations there, I think U will be much. U will be, this is just a minute. The image is 5. Okay. I have replaced this. This should be 5. This should be 10. Okay. So we will get U as minus 30 into 10 divided by 5. Or can I say minus 60 centimeter? Yes. So we got the value of U. We have the value of V. Now let's use these formulas in our mirror equation. Let's substitute it here. So 1 by F, we want to calculate F. So U is how much? Minus 60. V is how much? Minus 30, right? So we know the process here. What we have to do? Equate this. Numerator should be equal. So we have to multiply this by 2 and divide this by 2. So I can say this becomes minus 1. Minus sign is there, right? So let's take this minus sign upward. It will be better. Or I can say minus 30 signs will get here. So minus 1, this is minus 2 divided by 60, or minus 3 by 60, or minus, let's say 1 by minus 20. So 1 by F is equal to 1 by minus 20. So what will be the F? F will be, let's say, minus 20 centimeter. Right? So where is the option? This is the option, minus 20 centimeter. So this is a small numerical. So only two formulas we are supposed to use. This is the mirror equation, very important, and this is the magnification. But magnification has the two formulas here. Those we have equated. Okay. So once you know the formula, and also sign conventions are also important, right? They haven't mentioned anything that take the V as negative, but they have mentioned that it is in front of the mirror. So if it is in front of the mirror, then we have to take the 30. Okay. Sure. So this is the question. If the beam of light is incident through the holes of side A and emerges out of the holes of the other face of the box. So this ABCD is a box, and there are many beams are going. Beams, we have studied this in the last section, right? What is beams? Beams is the group of rays, we can say, right? So these rays are going inside. Normally what should have happened? They should have came as it is, right? But it is not happening. So they are coming like this through this small hole. So who can do that, right? Can it do the mirror? Can mirror do these things? Obviously, we know the mirror. What mirror does? Mirror reflect the rays. So if you keep the mirror here, these rays will never go outside. They will come back like this, right? Parallel. Okay, so it cannot be mirror, right? So mirror is not there. Prism, we don't know about the prism, so don't worry about that. If you keep the glass as it is, we have studied about the window, right? If this is the glass, light rays would have gone straight in the straight fashion, but they are not going into the straight fashion, right? So glass is also not the option. Lens, yes, lens is there. We haven't studied the lens. We will study in the next session. So if the lens is there, yes, then if these are the rays, consider if lens, this is the concave lens. We don't know it, but doesn't matter. We are anyway going to study it in the next session. So just remember, it's a convex, no? Yeah, this should be concave lens, right? Or convex lens in this case, right? So don't worry about this. We are anyway going to study this one. So just right for now, right? Just remember that there must be some lens inside that to get something like this. Okay. Okay. So our answer will be convex lens in this case. Okay. Sure. So we have studied today about the mirrors, plane mirror, spherical mirror. What is the equation for the mirror? What are the magnifications? Right. So if you do have any queries, post them in the forum, right? And in next session, we are going to study about the refraction. So we know about the reflection, right? Plane mirror is reflection. Refraction means what? Whenever light is coming through the glass surface, or consider the water, light going into the water, how the light behaves, right? What will be the path that we are going to study in the next session, okay? So anyway, we'll stop here today. Thank you very much. Have a nice day.